Today I'm going to do a little overview of system design. You know, as I dug into this, I realized this could be a whole series. So I'm going to try to hit a number of points and, maybe that will pique your interest and you can look at it a little yourself. So just to know who I am, I started during the first .com boom in the US. So I started '99. I was lucky to avoid year 2000 work, was part of Anderson Consulting's Internet Center of Excellence. Now that's Accenture. Really began as a full stack Java dev, but I've also done C++, JavaScript, C#, Python, and Scala in various roles. I went into the insurance industry after everything collapsed and was a voice over IP architect there. Since then, I've done various backend services and mobile and enterprise software. And I've done a bit of study on system design, so hopefully I can bring a new angle to you. And one of the interesting things about software is there's really nothing new under the sun. When I started, we just were submitting forms at CGI. That was the first integration I ever did. And then we went to SOAP, and now we're back to REST. So software doesn't sort of linearly move forward. You'll see one idea, and then people will look at its flaws, come up with something totally new. But then they'll say they went too far, and they'll sort of go back, but little improvements along the way. What we're going to look at here is why do we care about system design? So we're going to hit some software design principles, and we're going to talk about keeping the lights on and scaling the system. And then finally, I'm going to get a little bit into data stores because, you know, things have changed a lot there now with NoSQL and just various offerings from cloud providers. So let's hop right in. Why system design? Okay, so this is something you may run into. We're all familiar with Agile now. So, you know, I've sometimes had very good programmers that get a lot of work done ask, you know, why are we spending this time up front? Because there's a little bit of tension with Agile, right? They're saying, hey, you know, let's just make sure the stuff passes all the tests, and you know, we can refactor it later. Well, I mean, there is a point to that. You have a little tension there, but there are very good reasons to do a little bit of design up front. And keep in mind, when I'm talking system design, this is designed for us, not for the business user, right? I'm not talking about waterfall where we're gonna, you know, go back to the business user and say, hey, 6 months ago, you said you wanted it this way, so we're delivering it this way. No. I'm talking about design that's gonna help us with non-functional requirements, which are the ilities, they sometimes call it, maintainability, scalability, observability. You know, these aren't things typically in a functional test, but they really can make or break the system. Also, in the real world, you're going to get pulled away often. Like priorities change, maybe your project gets frozen for 6 months. If you're lucky, you'll be the one coming back to the project. But, it could be someone totally different on it because there's another priority that they want you on. But even if it's you, if you left this in sort of a halfway state where, oh yeah, we're gonna refactor it later, but right now it's like just junk, right? It might pass tests, but it's not easy to work on. You're gonna forget. It's going to just lead to a lot of time wastage when someone has to pick that up. And also, pager shifts are a bummer, and they're going to get worse. So we need to think about how easy is it to troubleshoot the system. All right, so I wanted to talk about non-functional requirements real quickly because sometimes this is really the whole point. For example, I worked on a voice over IP system in the insurance industry. We bought this off the shelf from a very major networking company, had a contact center solution. This was to replace, they used to have hardware automated call distributors. If you had like an inbound call center, that would distribute calls between your agents. Well, the typical use case is, you might have a couple levels of support. You might have a sales center where any salesman can handle any call. So they're thinking, less than 20 groups that you need to route calls between. But we had a situation where you're routing based on what licenses the various agents held. So we were in 49 states, and then you have several other groups that you need to handle. So we were well beyond the what the system was designed for. And whenever we would call in, they'd just say, oh, well, you're beyond capacity. So a lot of what I was doing there is not real programming. I had to figure out how to hack in a new JVM into their system, basically had to hard link into where their location was. I did a lot of looking at JVM source code to find undocumented switches. All this is very interesting, right? But it's not really, iterating on client needs. It's just making sure the system doesn't fall over because we added some new offices. System falls over. It doesn't matter how it works under ideal conditions if when a bunch of people call in, it falls down. Similarly, let's say you work at a retailer, especially in the US, you can say, oh, everything in here, it passes all the tests, and it's going to work 364 days a year, but Black Friday, it's going to fall over. That's not going to be acceptable. And another example would be if you're on a website where there are literally billions of pages, how do you get that all seen by Google? How do you make sure Google gets the right, schema data, tell it accurately what's on the pages, make sure Google's not wasting crawl budget on multiple versions of the same page? So this is SEO. People understand SEO, but when you do it at this scale, that becomes the entire problem. So let's hit some software design principles quickly. A lot of what we're doing when we're talking about software design is we're making sure that the impacts of changes are local. Basically, you change something in this class, it's going to break something in this class. That's really where a lot of the advances in software design, that's really what you're trying to do there. So I'll go over Robert Martin's solid design principles. That's Uncle Bob. He's a very good resource. Composition over inheritance, how testing can help us design better, and just a reminder that objects don't have to map to the real world. So the code locality, some of the benefits of this are when you're onboarding someone, they don't need to understand the whole system. You tell them, hey, we have tests here. I need you to change something in this component, and they can go in and make that change. And, you know, slowly they learn the ropes by doing these sort of bug fixes or enhancements that are fairly low risk. Also, if your project ends up being a priority, someone's going to ask, hey, what if we loan you like 3 more developers? How much faster can you do this? Well, if you did it, if your whole program is one class, you know, it probably won't make things any faster to add programmers. But if you have code locality, then you can have people working on different things, because face it, even though Git has made merging a lot less of a pain, it's like on a bug fix, that's going to be fine. But if you're talking adding functionality and people are in the same files, it's going to get messy. So single responsibility principle, a class should have one reason to change. A way I like to look at this is, logically, could more than one person work on this? If so, the class is too big. We need to split it into smaller classes. Like we have some sort of discount class that arbitrates between discounts, applies discounts. There are different types that both need to be arbitrated and applied. And then you do something else with all of these results. If that's one class, it's too big. You can go ahead and you can break those pieces out into smaller classes that are sort of used by one larger orchestrating class. And a surefire sign of this is you're making too many assertions in your unit tests. Sonar will actually flag this, at least in some of the setups I've seen, where they say, oh, you have 25 assertions here. Probably you need to test a smaller unit of work. Open close principle, the class is open for extension, but closed for modification. A good example of this would be a class that takes commands and executes them. So that class itself, you're not going to modify it, but you could send it a different type of command, and so then you're changing the behavior without making a change to the class. Liskov substitution principle can sound complicated, especially some ways that can be stated, but it's very simple if you don't try to formally define it. It basically says, hey, birds can fly, so let's instantiate an ostrich and have it try to fly over a chasm. Your ostrich can't fly, it dies. So basically this is saying, hey, if you have a class, you need to be able to do everything for the super class does. Now, how do you get around this? Well, interface segregation is a good way to do it. Basically, so Object-oriented design, really an object is data and the behaviors that go with that data. It doesn't need to map to a real world object. So you can think of interfaces as sort of a view to the object, and you can have many finely grained interfaces. So you can, you know, implement multiple interfaces. Let's say, so we're not going to have an interface bird, we're going to have an interface flyer. So now anything that can fly, that's going to be able to cross the chasm. And then maybe the bird does other stuff, like a bird is an egg layer, a bird can molt. So we have other interfaces that define that behavior. So the client of a class just needs to know about that part of the interface that they care about. Dependency, injection, new is glue. High-level code should not be dependent on low-level code. So what this gives us is we can control the direction of our source code dependencies in this way, because we can have the class only use interfaces, and then some other mechanism injects in the actual concrete instances. So once we start, building bigger things, this can matter because it allows us to break dependency cycles. And it allows us to swap in new implementations more easily. Like maybe you have a repository that was depending on, let's say your core code doesn't really care how you get your order object. Maybe it's from a database, maybe it's from some NoSQL setup. You can swap that out. Okay, so I've sort of hit on this. You should prefer composition to inheritance. Like a car has brakes, it has an engine, right? So should you really have like an electric car class and a internal combustion engine car class, or should you just put a different engine in? It's going to be easier to work with normally if you don't have that deep of a dependency, an inheritance tree. So just try to put things together rather than define them simply in is-a relationships. So testing can uncover code smell. Yeah, if the class is hard to test, you've probably broken one of the earlier rules, and that is why, one of the reasons why test-driven development, could make sense. I haven't seen pure test-driven development done anywhere, actually, but you should at least be thinking about how you're going to test the code, and I would get some real simple tests in quite early in the development. So some people say never change the class under test. I'm not a purist. If you have to, do so. For instance, you can go ahead and make methods protected, so you can just test the protected method. Keep in mind, if you're doing this sort of thing a lot, it may mean that really you should auto another class and have that do what the protected method is doing. And then you can just mock out in the main class, you're mocking out all these auto-wired components and making sure they're called with the right values. And then you unit test those components in isolation. So this also sort of points out it's a bit of a problem if you instantiate really complex objects in the middle of one of your methods. I believe you could use something like PowerMock to to even mock a new, but there are limitations to that sort of thing. It's similar to mocking a completely static object in that it's maybe not there in plain vanilla Mockito, and I've actually found in some situations you run into class loader issues, even if you have the ability to mock statics. So really follow good design practices, and if you're in Java, just auto-wired it. It's going to give you a singleton, or whatever other language you're in. There's got to be a method to do that. So mocking, if you're in Java or a JVM language, like, Scala can use Java libraries very easily. Mockito just has a lot of market share. I know I've seen another that I thought I liked better at first, but everyone's using Mockito. And actually, when you really dig into it, you can get a lot done with Mockito. So the then answer allows you to basically, you get an invocation object. You're going to be able to get the arguments to the method with that, and then return whatever volume you want. So very flexible. Similarly, you have the arg that argument matcher in Mockito. You whenever you do, you're basically, let's take a step back. By mocking, I mean we aren't using real objects. Like anything that is not the class under test, don't use a real object. You can if it's just a simple data object, because that's really just like a C structure, not a real object. But anything more complicated than that, mock it out. And basically what you're doing then is you're saying, when you call a method with these parameters, here's what you do. Well, you can get very flexible with that. There's an arg that matcher, which is basically a Boolean valued function where you take the argument, you can do anything with it. And already there are ham crest matchers, so you can do like contains, but you can do things like instance of. I mean, it's a lambda. You can do whatever you want. And then the final bullet point here is I was mentioning before, sometimes you can run into class loader issues when you have statics going. So if it is code that's not directly under your control, say it's in a library, another team that is working with that, you can just create an interface as sort of a wrapper. And so say you really want to call static class original method food bar. You do that just like this. Basically, you pass that, you're making a functional interface here. So essentially, you never created a concrete class for this, but just right there with the lambda, you're delegating this call, it's going to get passed. Problem. I'm looking at my time here, so try to get this done quickly. Defaults, know your language, and the defaults, you don't have to trust them. I mean, they're going to be reasonable, but for instance, back when the concurrent mark and sweep garbage collector was out there, I never ran into a single case where it wasn't the better than the default collector. Now, granted, VoIP and web have some similar characteristics, but just saying, those are two pretty big use cases. So don't be afraid to tweak things. Another one is, Java util concurrent, use it when you can. A good way to do things where you don't need the result right away is to throw it on some sort of executor. Now, the executors class has a number of utility methods, but in most of my use cases, I prefer to create my own executor because basically it's something I do need done. It has to be done, but it doesn't have to be done right now. However, I don't want to take up too many resources on it. So a lot of the default classes are actually unbounded. They're either unbounded in the length of their work queue, or they're unbounded in the number of threads they can spin up. Now, if you actually construct your own thread pool executor, you can specify these things. I don't really like to have anything unbounded as a rule because even if you don't exhaust all your resources, is it the most important thing in your system? If it's not, then it should be throttled. So, and plus, you know, there's always context switching overhead. So maybe you don't want to have an unbounded number of threads. And here, a good way to throttle is, again, this is not default, but the caller runs policy basically says, hey, if we've run out of threads you allocated and we ran out of work queue, run it in the main thread. Because basically what that means is your producer is outrunning your consumer. So with the caller runs policy, you're going to go ahead and run on that main thread and give some of the other threads a chance to catch up. You know, understand lambdas. When you're talking about a stream pipeline, I really like to think of them as sort of a super SQL. You basically have a stream of data, and you're, instead of bringing that data to behavior, you're bringing behavior to each piece of the data, so you can filter and then you map on that, and then whatever gets through, you can perform an operation on it. And it's also a good way. There are a lot of cases where I've showed you before with like Mockito, where you can use a Lambda just real quickly, bring a little bit of behavior. Be careful with this because a lot can be done on a single line. So I typically don't like to create a body in my Lambda. Like I'll just call another method, and that way the single line's not too cluttered. People can walk in and look at the individual methods and just try to make sure you're not doing too many pipelines in one place, split it up, you know. You want a complexity per method. Also, optional is getting better. If you ever have a chance to work with Scala, you'll see people in Scala sometimes, you know, they're not even using if-thens because, you know, they're optional. They can just say, hey, if it's not here, do this behavior. Logically, it's an if-then, but they're doing things in a more functional way. So Conway's rule, basically, the code is going to mimic the organization. So if you have like a business team that's dealing with recommendations, a business team that's dealing with orders, the development teams are probably going to mirror that, and you're going to have these components in your finished product. This is probably more true than you want it to be. For example, let's say if you have a cross-cutting concern like search engine optimization, if it's a huge company with many teams and you want to just sort of do some proof of concept, you might find that it's easier to put some sort of proxy up in front of the whole website and then modify the response to do your little proof of concept, because there's no way you can wrangle all those teams. And then once the proof of concept's done, maybe you can build something better where every team is calling into this service. But yeah, there's going to be inertia around Conway's rule. Release together, reuse together. This is sort of single responsibility for components. A lot of what we've already talked about sort of scales up and minimize dependency between teams. So this goes into architecture. I'll just touch on this. You want to defer decisions, and dependencies point inward. What I mean by this is your interfaces are going to be in your business rules, and you're going to use dependency injection to get the concrete cases. So like UI, persistence, those are not tied at the code level to your business rules. They're outside, so that means you can swap out. Like basically you can use your dependency injection framework to say, hey, we're not going to do that anymore. Now we're going to MongoDB. Nothing changes in your business rules. Keeping the lights on. All right. Devs have to do pager shifts now. For a time, there were like dedicated support engineers. I see that going away. And frankly, if programmers are doing their jobs well, businesses can cut people and everything still runs. And we see this right now, like once one business does it, it gives everyone permission, sort of. So we're seeing a lot of layoffs. And so I mean, the obvious downside of that is you're sort of mortgaging away your ability to iterate quickly on business needs for the future. One thing that's perhaps, since we don't have dedicated support organizations now, you're going to have fewer and fewer people supporting this. Now, if you have to support something once a week, that's one thing. But if it comes to where, like, during US hours, you are the guy supporting this, like, are you never ever going to go out and have a drink with friends again? At least in the US, they aren't paying you to be on call. So are you really going to suspend your life for them? So you need to be able to do stuff quickly, because you're not waiting around for things to break. Feature flag's a good way to do this. You get the code pushed out there, but it's never going to be invoked. So this sort of allows it to bake anyway, and you see that just having this component in your system isn't breaking anything. Then you flip on the feature flag and the users can see it. So then, if you're on this duty, you get a call in the middle of the night, turn this off, and deal with it in the morning during work hours, right? So also important to eliminate false alerts. It's just as bad as having no alerts. If you're getting alerted every night, then you're going to get alerts. So really need to look at that. A lot of logging. Hopefully you can buy this. Splunk, New Relic for monitoring. Unless you're in business of handling log shipping, it's probably money well spent to buy this, because nowadays you have logs coming from all over. You need to get all of them, put them somewhere, and be able to query them. Just remember, your services need to be using some sort of correlation ID so we can track through the system, because one user request might map to 6 different requests of microservices, so you want to be able to link those together. Code quality, Sonar is a good example. This is sort of like, or even find bugs. I think there's a new version of that now, but basically these things look for code smell, code that compiles but probably isn't great. Now, I would say devs should always be able to override this, and it should be a process where you get another dev to agree with you. But frankly, a lot of these rules are not really universal. I mean, you can force them to be universal, but there's no benefit. Like sometimes breaking the rule is the easier way to do things. And need to take PR reviews seriously, because just know what else is going on. So if you're the one on pager duty, you have some idea. Concurrency, consider immutability, going back to like something I learned from Scala and brought back to, in Scala, they aren't typically mutating stuff. They just build a new thing when they need something different and maybe add one more thing. But JVM reclaims awfully quickly, because basically when you're in Eden or the survivor spaces, you're just not going to be copied to the later stages. And so really objects are called once they become long-lived. And it's sort of one of those premature optimization things. Do you really think that object creation is your bottleneck? I haven't seen that to be the case normally. And use proven libraries. Okay, scalability. We could talk about this quite a bit, I think. Horizontal versus vertical. So I made the database here because that typically is a vertical situation. And there are ways around it nowadays. But there's only so big of a machine you can get. So really what you want is horizontal scalability, where you can have a bunch of machines doing the work. And even better is if your application is using microservices, then different components of the application can be scaled independently. And really, it's the cloud that has enabled this. When I started, we would order a server from CDW, we'd get it in a week, and then we'd have to set it up in our racks at the colo. Okay, obviously at that point, you can't really take a huge advantage of ability. It's going to take a while. You're going to need to anticipate. So back in that time, there were a lot of application servers that did session replication. This is really quite inefficient, because if you have 3 servers, all 3 servers are going to have the objects from that are on each of the others. So you're eating up your memory really quickly. So if you need session state, perhaps you should put it in Redis. You could do memcached, but Redis allows some more complex stuff. A lot of times people just put what they need in the database, or you know, say a lot of times you'll have a shopping cart service that, you know, it hides whatever it's doing from the rest of the application. You just know you query the shopping cart service, and that's taking care of that shopping cart for the session. And that's what allows you to build out horizontally. Caching, is 5 minutes a big deal to you? Many cases it's not. I mean, if you're, well, let's say you were going to Amazon, right? And you're looking at some category on Amazon. Do you need that category to be up to date at all times? Because I guarantee with Amazon, for 30 seconds, that's going to that cache is going to be hit often. And every request costs you money. Sure, CDNs cost money to the content delivery network, but it depends on how it's structured. Sometimes just getting the CDN costs you the money, and the cache hits are free. So take advantage. And one point here, hey, the biggest free news site in San Francisco was obviously running WordPress. I suspect it probably still is. It's just very customized now. And a lot of the web was running WordPress. Is PHP like the #1 scalable language? No, especially the way a lot of these PHP hosting services work. Because in many cases, you're not even on your own host. I'm sure SF Gate is, but in many cases, you're sharing a server, so they're not even using the best gateway to PHP because they're more concerned about security between the different websites. And how do these withstand the load? They're caching. They write to the disk, and they're doing some really complex stuff with mod rewrite. And they're saying, hey, say you have a blog, the 10 most popular blog posts, we're going to say that's good for a whole hour. So now, like, they never run through PHP for that hour. They're reading from disk. I'm going to blaze through this, just let you know, hey, HTTPS does cause you to be unable to use HTTP caching as often on these shared caches, but it's still worth knowing about, especially like the stale while revalidate allows basically the cache to update while giving you the old result. Plus, all this still works on the client's browser, and it will work if you have a CDN set up correctly, and if you're on one of the cheaper CDNs, this is probably what they're using. You get the more custom stuff when you pay big bucks. On your side, Memcached or Redis, if you can't take a network hit, use Caffeine. That's from Google. Basically, if you're familiar with a linked hash map, this is a concurrent linked hash map. So this is another case of knowing your libraries. Concurrent hash map allows multiple threads to access a hash map without contention. So that's way better than synchronizing on a hash map because, yeah, if you have to lock it, that's a huge bottleneck. Okay, load testing. A lot of organizations don't pay for this. Kind of a pet peeve of mine because I used to do a lot of load testing. I was working with Load Runner, so I mean that's probably bigger money than anyone wants to spend. But the other side of this is, hey, do you want to crash on Black Friday? So Gatling, JMeter, those are some free options. Just make sure you're simulating traffic well, throwing in some randomization, and verify results, because a lot of times under load, something funny may happen where like the site doesn't even realize it failed. It will give back a 200, but the data's wrong in it, especially if you have race conditions, like it will just give an incorrect result, not fail to give a result. But Load testing, it allows you to find the bottleneck, fix it, um, use profiling tools here, but you want to avoid premature optimization in many cases. A lot of times you don't know where the bottleneck is. The way you find out is by load testing. All right, let's see. Streaming versus message queues. Thought I'd point this out because message queue and Kafka, at first glance, they're pretty similar, but there are some differences here. Like, for instance, you can seek backwards in Kafka, but like with Spring, like reading forward in Kafka, very easy with Spring. You just have a Kafka listener. If you're going to read backwards to retry something, it's a big pain and it's not even recommended. What I've seen people do is basically if there's an error, they throw it into another stream that gets checked a little less often. Then you cascade it down into another, and then maybe finally you have a dead letter queue like you would in any other message queue. Both of these, you're putting stuff in. You have producers that's putting stuff in a queue or a stream, and you have consumers reading from it. But when you have a real message queue, you have a smarter publisher. It can do a lot of routing. Kafka is dumb. It just throws it into the queue, and it's your consumers that know what to do with it. Typically, you're going to have high throughput. It's not optimized for transactions. You might have more than one thing being done to the stream, like IoT is a good example because you can get just a whole mess of data from IoT. So maybe you have one consumer group that's logging it, another consumer group is transforming it or doing something with the data. Another example I've seen is back in the day, I don't know what their architecture is now, but New Relic was using like a dual Kafka setup where the agents were just doing some real simple stuff with the data initially, and then it went to another Kafka queue, and then over there they were doing aggregation and so on, the heavier stuff. We're gonna blow past that. So data stores and cap. So this is theory. Reality gets a little messier. So we're just going to say right off, databases don't deal with partitions. Not really true anymore. But that theorem is basically telling you how does the system fail. So one of the ways that a distributed system can fail is you basically get two leaders elected. Like if the heartbeats go wrong, like one guy thinks he's the leader, the other guy thinks he's the leader, and they each start processing requests. Once the split brain goes away, what happens? So Cassandra sacrifices consistency in this state, and MongoDB by default sacrifices availability. Like it will try to just not do anything if the brain is split, whereas Cassandra will just be like, well, I tried, which, if you're talking about likes or whatever, who's a like? Is it a big deal? Now, I said it's only part of the story. You can take a look at Jepson.io if you want to see like some stress testings of these systems. He's managed to break things that were considered pretty solid, and he's also found out some interesting things about consensus protocols. A lot of these distributed systems are using a limited number of protocols. You have Zookeeper, You have yarn. Basically, like there's usually some sort of consensus protocol that's going to try to keep the cluster together. Okay, so Cassandra, bring in nodes. You make that call, and depending on the redundancy factor, it's going to flow around that ring and create copies of your data. And the dotted line is like if I'm trying to retrieve, the dotted lines are retrieval. So the original node, whichever one you hit, is going to try to figure out where your data is stored based on a partition key. So it's important to have a partition key that splits things up evenly. I sort of blew past before the celebrity problem, but this is a good example here. Like, let's say we wanted to distribute all Avenue coders like their Twitter like graph or retweet graph and Elon Musk, right? And we wanted to distribute that between servers. Well, you know, what you hope is you figured out a way that Elon Musk gets his own server, and like everyone else can share one server because Elon's getting way more retweets than all of us. And it's, I mean, this is a common problem on every social network. There's going to be some super spreaders, so to speak. MongoDB prefers consistency by default. It supposedly has ACID, but that has been broken. I don't know where they are, you know, but AFER did manage to break that, so there was a bug reported against that. So this is preferring consistency. And one thing I was noting on the last slide as well, even if you're not talking about a failure, Cassandra still would rather answer you than wait for consistency. So it's an eventually consistent system. MongoDB is going to try harder to get you the right answer before it returns, which means, of course, there's going to be greater latency. Now, here's the thing about going with these solutions. It's a totally different way of accessing. MongoDB is obvious at it because you're storing data as documents and they can be nested. It's almost hierarchical, you know, like way back in the day, hierarchical databases. Cassandra, though, looks like a DB, but it's not at all. I mean, it's called a columnar store, but you can only query on a key. You can't do joins. So you need to design the thing based on your queries. So if you're going to query a table two different ways, you're actually going to have it twice in Cassandra. You're going to have one on the one key you're going to query by, and you're going to duplicate everything all over again on the other key. So when you're doing this big data stuff, you're not normalizing the data. I mean, you're going to have more data because it's just not as efficient as a normalized relational database. So you're going to process differently too, because basically if you're not doing joins, you're probably going to ingest this and do some sort of map reduce or Spark operation. So don't forget about good old RDBMS. I was working for an ad tech company before I came here, so about 4 years ago, and they were doing at least 100 terabytes on MySQL. And yeah, the DBA mentioned petabyte. I'm not sure if we were really there, but keep in mind this company was basically taking data from Google, from Bing, from Facebook, and like managing ads and campaigns for these clients. So I mean, there's a lot of data from those companies. So they use shorted MySQL, and this actually outperformed Pig and HBase, which brings me back to one more thing that I kind of blew through earlier in the interest of time, but one of the reasons you really want to have be able to break things into components that aren't dependent on each other is I'm really seeing if a team is doing three things, it's a huge problem. Like even two things, you need a pretty solid team. But for instance, if you're going from a monolith, you're going to break that into microservices. You're also going to change to using Scala primarily. And you're going to change your backend to some sort of big data system. I would say, without even knowing how awesome all these programmers are, that's going to be way behind schedule. I've seen it over and over again. You know, that people are usually quite talented. And the way to get around this is if the monolith were already broken into microservices, these other things could be done piece by piece by each team, right? So the more your components are broken out, it allows you to do different things at different paces, and it's not going to put the whole project at risk. And I was going to mention data lakes and processing, but we're getting so close to time here. I just wanted to see if anyone had some questions.
Yay, questions, anyone?
And I can come back on the lunch and learn if we really want to dig into one of these topics. So, you know, if we probably have like a feedback form, if you can just say in there you want to hear more about this thing or that thing, I tried to dig in more. Yeah, at one point I thought this was going to be too light, but then I went through it again, and boy, it's hard to cover it all.
Yeah, it was perfect, and for sure we can do a lunch and learn to talk more. I'm sure everyone will like this topic. So Tom, thank you so much again. Your presentation was awesome.